Hi, hello. So welcome to lecture B10. Today's topic is cloud containers and config management. My name is Richard Huang, and I got a slightly better mic, so hopefully that helps. Today's topics are virtual machines, containers, and configuration. And so the main ideas for today are basically, how do I make sure everything is configured properly and stays that way? How can I make sure that system performs reliably with minimal downtime? And when everything breaks, how do I fix it? And so the first topic today to help answer those questions are virtual machines. For those who don't know, virtual machines you can kind of think about as like a computer inside of your computer. And so it's basically like this abstraction layer that basically helps abstract away the physical hardware through software emulation. And this layer is usually called the hypervisor. And you can run multiple VMs on top of this single hypervisor. The advantage of this is that, for example, if you have application A and application B, one might need Python 2 for some weird reason, and one might need Python 3. You may have library conflicts like that. And so being able to separate these applications into their own VMs helps with stability because there is no connected library between them. And so therefore there's no library conflicts. And because of that, there's also better security because of the isolation. However, there is some overhead because of the fact that you need a different OS for each VM. And there's also the overhead of the emulation for the virtual hardware for each application. And the other thing is it does take some time to boot up. It is slightly better than like a normal computer, but it still does take a decent amount of time to boot up. But yeah, so this is basically like a diagram of it. Where's my pointer? There's my pointer. I can think of it as like, this is your hardware, like your CPU, your memory and stuff. And then a hypervisor just sits on top of that and abstracts all of it away from the applications and the VMs. And each of these tiny boxes inside the blue square is a VM. And you can see here, each VM has its own emulation of virtual hardware. And then on top, you have guest OS. And then on top, you have the actual running application. So you kind of see it's isolated, right, within each individual box. However, you do have this extra overhead within each VM in order to run a different application. But that's the VM. And so just as an aside, there's actually multiple ways to do abstractions like this. So for example, at the hardware level, you have SMT, hyperthreading, and multi-core computing, SIMD, which you probably will learn in 61C or have learned. There's also process level abstractions such as virtual memory and multi-threading. On the application level, you have sandbox applications. And in the operating system, you have, namespaces, kernel level isolation, BSD, jails, Solaris zones, Linux containers. And for full virtualization, you have KVM, VMware, Xen, Hyper-V, and so this typically does hardware virtualization with Type 1 and Type 2 hypervisors. And yeah, so that's just a quick brief intro to virtual machines. So we'll be moving on to containers. And so containers, you can also kind of think of them as like a lightweight VM. They're technically not a VM, but you can kind of think of it similarly. We won't get too deep into how exactly they work, but their goal is basically to provide like lightweight isolation by sharing some code, like libraries and hardware with the host. So it's a lot faster to boot, like way faster, like seconds or even less sometimes. And you can basically, it basically helps make it easy to package applications for consistent deployments. And some of the most common ones that you may have heard of are Docker, Rocket, or RKT, I think that's how it's said, LXC, or Linux containers. But yeah, I don't know if this is true, but I think this is the only class at UC Berkeley that uses Docker still. But it would be nice to see more classes use it. It is pretty cool. But yeah, so since Docker is the most popular one that you've probably all heard of, we're going to mostly talk about that. So Docker is basically this container platform that is backed by OS level virtualization. And what a container is basically a running instance of an image that's been loaded into the memory. And an image itself is basically just a file that provides a template for spawning new containers. So it's like kind of like, you can kind of think of an image kind of like as a cookie cutter. And then this basically helps you create cookies, which are the containers. It's like a bad analogy, but you kind of get the idea. But yeah, so how do we create these? Oh, first let's go through, actually, you know what? Let's go to this first. So how do we create these images? So you create these images using something called Docker files, which you may or may not have heard or seen. So you can see here, basically, we're basically using the Ubuntu image as our base image. And then we do some system updates and install some packages. So in this case, we're updating, we're installing Python 3, and we're also installing pip. And then we also update pip. And then we install Flask, which is just a web server. You don't have to worry about what exactly it does or is, but it's just a web server. And so we can also add local files to our server, or to run the server to our container, by doing something like add hello.py into /app/hello.py, and then we can set the working directory to /app. And then all we have to do now is just inform Docker that we're going to use port 5000, and then set the entry point for Flask to the hello.py, and then just do Flask run host localhost, and that's it. Yeah. And to go back quickly, some quick Docker essentials for when you're using Docker. And if you want to pause this, it might be a little easier to read it. And you can always just, man Docker if you want more explanations of what they do. But yeah, we have Docker search, basically searches the Docker hub for just pre-built images, like the Ubuntu one we looked earlier. That's basically like a pre-built image. You can also do Docker pull to pull the images, Docker images, build, run, PS. Yeah, I'll let you look at it on your own time. But I can do a quick demo as well of, for example, this. So let me just pull up the Decal. Yeah, that's the right one. 2, 3, 4, 5, 6. Over here, we can see we have a Docker file and a hello.py. So let me just show hello.py quickly, just so everyone knows what it is. So all we're doing here, you don't really have to know what exactly this does, but it's basically just a Flask web server that just returns hello.world when you go visit it. Yeah, that's it. Nice and simple. And so what's the Docker file? So I basically just copy pasted this over. And so the hello.py that we referenced, which you probably were wondering about in the slides, is basically just this hello.py. And yeah, so how do we use this? So we can actually build the image. So by saying docker build, right? And so we're saying like build within this directory. So we'll just search for the Docker file in this directory, and we want to tag it with a name. And so in this case, Linux Decal b10. And yeah, so this is really fast because I already built it before. But you can see through the steps here, right? It grabs the Ubuntu base image, runs the updates, installs Python, pip, Flask, adds our hello.py, and then we just expose the port 5000 and then tell Flask to run this. And yeah, now we basically have an image. And that to actually see the images, we can just do Docker images. And you can see over here that, there we go. Oh, there we go. You can see over here that we have the Linux Decal-b10 image that we just built, or I built earlier. But yeah, so that's that. And how do we run the actual Docker image? So all we have to do is just call Docker run, and I'll explain this quickly. So the -p just stands for port. So all I'm doing is saying I want to connect my localhost port 8080 to the container port 5000 where our web server is running. And the --rm, this is just because Docker keeps containers that are stopped, and I don't want to keep this one around because I don't need it. But yeah, and then we just specify the image, Linux Decal b10, and we just click run. And yeah, it's working. So it's running a Flask server over here. And if we just open Chrome, right, and go to localhost 8080, you can see hello world, right? Like it's working. And if you just like refresh a bunch of times, you can see that we're getting requests over here. But yeah, that's basically how you build a Docker image. You run the Docker image as a container, and yeah, cool stuff. So yeah, that's Docker. And so in the industry, lots of people are using like a bunch of containers, and they have just like thousands or possibly millions of containers to manage. So how do we manage all of it? That's where container orchestration comes in. And so basically container orchestrators help us make sure that we have A, the right amount of containers we want, B, the containers on the proper machines, and C, we handle failures by restarting when they die. I'm not going to get too much into it, but through distributed systems magic, we recover from failures by having multiple masters, distributed key value stores like etcd and stuff like that. But yeah, so these are some of the more popular ones that you've probably heard of: Kubernetes, Mesos, Marathon, Docker Swarm, Kelda, If I do remember correctly, I think OCF runs on Kubernetes, and we actually recently were using Mesos and Marathon before we moved to Kubernetes. But yeah, that's that. So with all these tools, how exactly has the modern infrastructure evolved? So you can kind of see here, this is like before VMs and before containers, we basically had this thing called a non-converged infrastructure. So apps basically ran on bare metal over here. So like we have this storage network, we have servers, and then we have these apps running on these servers. And the issue here is there's no isolation because these apps run just side by side on the servers. And so there could be, conflicts, library conflicts and stuff like that. And there's also no easy differential resource provisioning. And moving apps is definitely a nightmare. If you've ever tried to move bare metal apps, it's not fun. Let's just leave it at that. Yeah. And compute management is also questionable to calculate. But yeah. So moving on, we introduced VMs. And so this is where we have converged infrastructure. So these apps, basically, instead of running on bare metal, we now have this layer of abstraction, which is the VM. And so these apps run on these VMs, which are provisioned by these hypervisors. And so this provides isolation and also provides differential resource management, differential resource provisioning management, same thing. But yeah, so however, moving apps is still a nightmare because of how virtual machines works. And compute management is also still a little questionable. And this is where we have something called hyperconverged infrastructures. And so these are basically where apps run on VMs or apps run on VMs or containers provisioned by the hypervisor technically. And these provide a lot better isolation, and there's still differential resource provisioning, but now there's also the fact that software basically manages all of it. You can see here that we now have this distributed controller that basically helps control these VMs and these stuff like that. Yeah, so basically software can now help move apps, software manages compute, and scaling is basically trivial, kind of like with Kubernetes. We can just say if we want more VM or we want more containers, we just say, hey, give me more containers, and it just spawn up. And so this is the current infrastructure that we have, basically, is that software manages everything. We have these layers of abstraction to help with that. But yeah, that's containers. So moving on, we have configuration, right? So with this huge scale, we have new problems. And these problems usually are composed of, like, if we have a million or a billion machines, like you can imagine at Google how many machines they have. It's probably crazy. But how exactly do we provision them? So they have everything installed once they boot. Like, how do we organize these machines to do the work that we want it to do? Like, even VMs on like popular cloud providers like AWS or GCP, I don't think they take 5 to 10 minutes now. It's probably a little faster, but it still takes minutes to actually provision and boot up. Yeah, so how do we recover from failures automatically from these things? And what happens when we can't recover from failures automatically? Like, these are the big questions that we have now with this huge amount of scale. And to help with this is where automated configuration management tools comes in. Oh my God, that was a mouthful. But yeah, these are declarative programs. So you basically tell it what you want, not exactly how you do it, but you just say like, I want this. And then the application figures out the how for you. It's really nice. And so you can basically define applications to install, files to include, users to create, and stuff like that. And you can also install different things on different classes of machines, like a desktop versus a server versus a mail server, or possibly even a printer server. And some most common ones that you may or may not have heard of are Puppet, Ansible, and Chef. I believe the OCF uses Puppet, though I don't personally have that much experience with it. I do use Ansible myself, and I actually have an example of it. If you guys want to check out, actually, let me see if I have it. Yeah, yeah, I can go through quickly, just as an example of what you can do. So basically, I have like this home labbing is like my hobby. I do some self-hosting stuff like that. So it's kind of a pain if I want to set up all these applications that you see here manually. So I basically use Ansible to automate all that for me. So over here, I just have this, it's called a playbook or whatever. But yeah, I just have all these apps, and I can basically just tell it what apps to install on my server or on the new server or whatnot, and it basically goes and does it. And for a quick example, I can pull up Plex, which is a media server. You can see here, meta. It just tells it what dependencies to install, for example, Docker, firewalls, what ports to open. And then for tasks, it basically, pulls in the, this is from earlier, containers, right? It pulls in the Plex container and it just tells it some stuff like what image it is, the name of it, restart policy, network mode, where to store data, time zone, stuff like that. And also to put the domain at where it runs. And yeah, I just have a bunch of services like these, and you can actually, my entire like setup is like this. So if I go to like plex.my website, this is my Plex server, which I host a bunch of media on and stuff like that. But yeah, there's a bunch of this. So for example, like I can go to like monitor.my website again, and you can see this is Grafana now, which is this boy over here. Yeah, and this basically just like has some basic monitoring information about my server. But yeah, so this is why configurations like Ansible is really nice because you can just automatically configure it and you don't have to manually do it over and over again, which gets really annoying. But yeah, that's a brief personal example of how automated configuration management tools work. And so since the OCF mainly uses Puppet, I'll go over that more in depth. So basically how Puppet works, you can kind of see this is like the Puppet platform. You have this single Puppet master, like we said earlier. We have these nodes down here that are running Puppet agents. And this Puppet master communicates with these Puppet agents and to basically configure them. And you also have these modules up here, which basically, like a Puppet dashboard, and you also have like third-party systems to interact with Puppet. But yeah, so how does Puppet work? Puppet, like I said earlier, it's an agent master paradigm. You can see here, agent master, right? So Puppet agents run on basically every machine that you want to be configured, and the master runs on only one machine. And so this master contains all the Puppet code that we want to write. And this code is split up into multiple classes or roles or however you want to call it, which basically defines different machine configs. For example, you can have like a mail server, like I said. And yeah, master can even contain code that actually defines the Puppet master config, configuring itself. And yeah, so this is basically the life cycle of a Puppet run. So to apply configurations, the master basically gets the information of the node called facts from a utility called factor. This is step number 1 over here, right? And then the master basically uses these flags and class types to compile manifests into a catalog, which contains basically resources and resource dependencies, and it'll basically apply this catalog back to the node over here, right? That's step 2. And then once this catalog is applied, it'll just generate a report that it sends back to Puppet, which basically just indicates the configuration is complete. And you can also report from the Puppet master for like third-party tools and whatnot if you want. But yeah. Yeah, so how exactly does like the communication work? So Puppet uses like SSL certs for secure communication, and you've definitely used this before if you've ever used HTTPS, and if you aren't using HTTPS, you probably should be. But yeah, it's based off of public key cryptography commonly seen in web applications. And to use this, Puppet runs its own certificate authority, or CA. So on the first run, the agent basically has its cert sign. And this is because that we want to prevent DOS attacks, because we only want to ensure that legitimate hosts have signed certificates so that communication is nice and smooth. And so some important definitions for Puppet are basically resources, right? Defines a resource that we want on the system, such as users, files, or service, or packages. And manifests are basically files with the PP extension comprised of related Puppet resources that achieve a certain task on the target system. And so classes are defined in the manifest, and they basically tell Puppet how to execute code in that class. So for like normal classes declaration, you can see we just say include some underscore class. For resource declarations, we basically say, allow overrides or class and then class name. And then for modules, they're basically just a collection of manifests and data, such as, facts, files, templates, whatnot, and they have like a directory structure. And so for example, there's the mail server module. And so this is basically a simple Puppet resource example of declaring a user. And so over here, we can see we're declaring a user with the name Harry, right? We want to ensure that Harry's present. because it'd be nice if Harry existed. And we want to give Harry a user ID of 1000. So we just say user UUID 1000. And then we want to give him the shell. You want to give Harry the default shell of ZSH. And then we also tell Harry's home location is /home/Harry. So now he's not homeless. So now here's the question. How do we give Harry a group ID of 2000 now? All right, it's not too hard. Think about it for a sec. Yeah, so we basically just say GID points to 2000. And you can also see other examples here. I'll let you look at that on your own time. But yeah. So what happens when Puppet fails? So when Puppet fails, it's not exactly the most graceful, but at least it's sane. So it basically just generates like a huge report that shows you where the error happened, and then the user just goes about debugging it and finding out how to fix it. And there's lots of reasons that Puppet can fail. You know, it's not perfect. You know, there's improper syntax, dependency failures, resource failures, such as, you know, out of disk or memory space, or when the Puppet master isn't running. But yeah, these automation tools do really help with configuration and provisioning of like tons of machines, so you don't have to do it manually. But yeah, that's it for lecture B10. Thanks for watching and have a good rest of your day.